All right, so before we move on to thinking about how we're going to make these organohalides, first we have to take a deeper look into radicals. So remember from our previous lessons, our radical is an unpaired electron, something like a chlorine with this electron. And so you want to review those notes. Remember the 3 steps of these radical reactions: initiation, propagation, and then finally termination. We're going to take a look at our radicals though, so make sure you remove that kind of stuff. And so the first question you might have is, what is the hybridization of a radical, right? On one hand, we have our carbocation, which we know is totally flat, and here it's attached to 3 things, so that's an sp2 hybridization. On the other side, we have our carb anion, which is attached to 4 different things, so it's sp3 hybridized. And so what about a radical? Well, the answer is it's somewhere in between. But overall, it's closer to an sp2 than an sp3 hybridization. So it's not totally flat. There is a slight angle to this radical. Draw this little orbital there. However, it can interconvert, flip, and flop back and forth very easily, similar to what nitrogen does. Right, so it's very close to planar. It's not exactly planar, but it's pretty close. And it quickly interconverts. And so what that means is that we have no stereochemistry here. And if your original substrate did have stereochemistry and you turned it into a radical, you delete out any of your stereochemistry, right? So if you start off with all R product and then you did some kind of radical reaction, you'd end up with some kind of racemic mixture. In terms of stability, it's similar to carbocations due to the same reasons of hyperconjugation. And so a methyl radical is the worst, right? You won't really ever see that. Primary, also really bad. Secondary, a lot better. Tertiary, pretty good. And then actually allylic and benzylic radicals are even better than tertiary radicals. This isn't necessarily true for carbocations, but it is true for radicals. So when we go from the left to the right, we become more stable. Right, and again, this is methyl, primary, secondary, tertiary, allylic, and benzylic. Right, why are these 2 more stable? Well, it's because of resonance. Remember to use your half hook arrows when you're showing this stuff. Right, so we have these resonance structures, which helps stabilize. Another thing that students like to do, which is bad, is try to put the carbocation on the vinylic position, and that is very bad. So the vinylic position is right on this carbon that's sp2 hybridized, right? And it's so bad that it's even worse than methyl. Right, so do not go towards vinylic. Allylic is good though, right? So know the difference between allylic and vinylic. Finally, another big difference between carbocations and radicals is with radicals, there's no rearrangement. So for example, let's say somehow you did form this primary radical. Should be very hard to do, but let's just assume you did it anyways. There's no way to rearrange. This will not rearrange. Right? Even though it's bad, it won't rearrange.